Quantum computing is more of an emerging technology than a widely adopted tech industry standard. But quantum is on the way, perhaps in just a few years, maybe by 2030, and it promises enormous changes to cybersecurity, artificial intelligence, and even a regular daily life. I'm James McGuire. This is Tech Voices, and I'm discussing the future of quantum computing with a leading expert in the field, Murray Thom, Vice President at D-Wave. Murray, really good to have you with us today.
Thanks, James. It's a pleasure to be here. I'm looking forward and kind of maybe even accelerate some of those timelines that you were talking about.
I thought you would want to because you're in the business currently, and here I am saying it does not happen yet. So that seems very unfair. We'll get to that. We can have a disagreement about that. Or you can clarify that issue. But I guess the first thing, I feel like I have to ask that very 101 question. What is quantum computing? And I'm reluctant to ask that level of question because most of our listeners, know most tech terms, but I think quantum is still something people are confused about. I know with classical computing, they use electrical impulses to do ones and zeros, and they hold data that way. That all makes sense. With quantum computing, I think they use subatomic particles, maybe particles of light, photons, held in place with laser beams. Maybe I'm making it up. It sounds very Star Trek.
No.
So what is quantum computing in terms that even I would understand?
Okay, and I mean, probably the thing to admit is that many of us in the quantum computing industry make it a lot more complicated than it needs to be.
Okay.
So in terms of how we're going to see it in our daily lives, quantum computing is energy efficient computing for hard problems. The idea for the technologists who are trying to, like myself, who are building these machines and making them available to businesses for their applications, is that we're using quantum effects to perform calculations that are too slow or too hard to do with classical computers.
Right.
So an enterprise who's dealing with challenges, maybe they're having a hard time moving into a new market or getting the agility they want as they're trying to maintain their productivity and their manufacturing processes. Those are the firms that are kind of looking to the technology and saying, how could I take advantage of this and actually help my business operate more effectively?
Right.
And so, there's a whole taxonomy of different quantum computing styles, but we probably, I would say the hardest question to answer is like how quantum computers work.
Right.
But maybe probably the question that's most on people's lips is, what can quantum computers do for me?
Well, true. And I think that's a really good question because maybe that's the question of the day. But for my own education, I think for the audience, it's like, okay, maybe oversimplify it. I know there are various different styles. So put it in simple terms, what's going on down there, like underneath the hood?
Yeah, okay. So if taking that statement I made before, using quantum effects to perform calculations that are too slow or too hard to do with classical computers,
Right.
as much as we don't understand quantum mechanics, to a computer, it looks like a resource. And it turns out there's multiple ways to use it as a resource for computing. So at D-Wave, we're building two different models of quantum computing, and those models are thoughts about how to take advantage of quantum effects. One of the models is called annealing. It helps the computer move between solutions more quickly. So if I'm working on an application like scheduling grocery delivery drivers, I might start with a random schedule, and that would be terrible. But then I want my computer to move to progressively better schedules, and the speed limit for quantum mechanics is faster than it is for classical computing. So it can help us get there more quickly.
Okay.
To contrast that, let's say with a second model, which would be gate model quantum computing, there we're using the quantum effects to allow the computer to store more information. So if we're trying to do molecular dynamics calculations, we've got a new molecule we want to consider as a new drug, and we want to simulate how its electrons are going to interact with our body and the elements in our body. Well,
Right.
we need to, those are quantum systems. So we need actually a huge amount of memory in order to actually calculate how they're going to behave. And a gate model system can use quantum effects to allow it to do that. And then once you've got that model in mind, then you need to think about, well, how am I going to build it? And this is where you get into the points that you were talking about, subatomic particles. There's folks who are using atoms,
Right.
electrons, photons. In our case, we're using metals that can actually circulate current with no resistance whatsoever. So those are called superconductors. Any kind of quantum mechanical system that can be put into two states, you can basically use to build a building block. It just happens that some of them, like superconductors, and some of the models are actually allowing us to get to near-term applications much faster.
So there are people using subatomic particles, and it sounds like you're using metals and probably they are like really, really tiny at any rate, correct?
Well, it's interesting because they're actually physically like fractions of a millimeter in size, which would be,
Yes.
thousands of an inch kind of thing. So you could
Sure.
actually see the the lines, on a silicon chip. The chips themselves are about the size of our thumbnails, and there's actually printed circuits on there. But what's happening is that in those metals where they flow current, is that you can make a loop which has current flowing in one direction or current flowing in the other direction, or both at the same time.
Right.
And because we can make it behave quantum mechanically, then we can use those behaviors, those effects, to help us do information processing better.
Well, that's the other part about what goes on underneath the hood that I almost understand. It's like there's a sense, not that it can do two things at once, but it can look at both sides of the solution at once. It's like it's not a one or a zero, it exists between those two. I know we're way down to the weeds here, but I find this kind of fascinating.
Well, when I'm talking with software developers, their reaction is like, how am I going to write a program, where my variables are in multiple states at once?
Right.
And actually there are communities of programmers who are actually very used to this. People who work in the optimization domain, people who work in machine learning, people who work in finance, they're regularly working on problems where the way they would solve a problem like a business logistics problem associated with like workforce scheduling is they
Sure.
would just declare the problem. So they would describe it in words and then they would turn that into code. And then the computer has to look through all the scenarios of all the business decisions they need to make. So that's the great thing about quantum mechanics is that if a computer is having to do that, looking through all of these different scenarios, the quantum mechanical computer can look through them much more quickly. That's what I mean by the speed limit's faster there.
Gotcha. All right. Well, then I want to ask you about what are the most practical real world use cases for D-Wave's quantum systems today? You've talked about that a little bit, but I guess sort of underneath that question is a sense of generally, I think it's thought like, well, there's quantum advances every month. I hear a new headline and it's like, wow, quantum's done this and it's done that. And, IBM is saying we're going to have a quantum computer that's going to be this large by 2029. So it feels like very much in the distance, but it's not that long from now. But then you're saying, oh no, we have clients in the real world right now. So it's hard for me to put those two things together. Like you have in real world clients and all these companies going, well, it's soon. We're going to have it soon, just a couple of years from now. So how do I reconcile those two ideas?
Okay, well, yeah. So the question is how to reconcile it, and what's happened is it's because the quantum computing industry has progressed in a very different way than, let's say, the classical computing industry, where in classical computing, a lot of the early companies kind of broke apart and reformed, and you ended up with several players on an equal playing field. Whereas D-Wave was an early player in quantum computing, and we've maintained our position leading this space for over 20 years. In fact, I've been with D-Wave I'm just celebrating my 23rd anniversary
Wow.
with the
Wait a second.
company.
You've been with D-Wave for 23 years.
Yeah, this is what an old timer in quantum computing looks like, basically.
I'm absolutely shocked that there have been people who've been working for D-Wave for 23 years. So first of all, congratulations.
Thank you, thank you. So what, like any competitive commercial space, there's a number of players with different technologies doing different things, and they're all competing with one another. But part of the difficulty is that people have a tendency to describe what they're doing as if it's the entire industry,
Aha.
and that's very confusing. I regularly meet with people who say, like, why am I hearing these different things from these different audiences? One of the key reasons for that is, D-Wave is building two models of quantum computers, Annealing and Gate. A lot of other companies are just building one. And
Aha.
Gate, for instance, which has those very powerful applications in quantum chemistry or in fluid flow simulations, it's probably 7 to 15 years away before it's going to be large enough to impact commercial applications. Whereas with annealing, it's impacting commercial applications right now. And so the
Aha.
subtext that I think most other folks aren't mentioning is that it's really their machine that's a little bit further away, but it is possible. We, D-Wave, have machines that are being used by our customers for their production applications. And that's why D-Wave is so very different from other quantum computing players in the industry.
All right. So what are a couple of real world applications then?
So that's a great question. And let's imagine that we had a spectrum in time where we had like some very interesting, exciting applications like the ones I was talking about that are in our future,
Right.
revolutionary applications that are going to change their application spaces. We're really focused right now on near-term applications, and there are several which are already possible and realized. So the places where those tend to occur with the, like most reliably, meaning that like if you look within your business in the area of like workforce scheduling, maybe logistics routing, you're trying to route a series of vehicles making deliveries, production scheduling. So you've got like a manufacturing plant and you're organizing a variety of manufacturing equipment and people and resources at different times,
Sure.
uh, or cargo loading and those kinds of transportation problems. Those are problems that are very difficult for classical computers, where our quantum and quantum hybrid technologies have really had a big impact. So to use an example, a grocery store company called Pattison Food Group, they own 13 different grocery brands. They have built two applications that they have in production right now. One for creating the schedules for their at-home grocery delivery driver fleet.
Hmm.
That's saving them 80% of the time it was previously taking them to produce those schedules. And then their second application is for organizing all of the workforce in stores who are trained to work in different departments, and the stores have, varying demand each day of the week and each week of the year.
Right.
There in that application, they're already expecting to save their workforce 50,000 hours every year.
Huh.
So really exciting because it's one of those things where you're solving a problem which is occurring throughout your business, and then you get this network effect in terms of the benefits as you're looking across all those resources.
So really, the applications you mentioned really sort of are workflow management. And of course, classical computing has been doing workflow management for many years and apparently just fine. But you're saying quantum can also do it, but just faster.
Well, yeah, and fine meaning it's the status quo, right? But
Okay.
what's happening, think about it from the perspective of like an energy grid, right? So if you have a central power plant in an energy grid that's just sending power out to, the homes and businesses around it through transmission lines, for a classical computer, optimizing that is really, really easy. If in fact if that is the shape of your energy grid, continue using classical computers for that.
Okay.
Because as the load gradually ramps up, you just gradually ramp up the power to meet it. So you're continuously changing things. You're not flicking switches from on to off, for
Right.
instance. And then the other thing is that the power that's going down the east grid for me, west grid, let's say, is not going to affect the power that's going down the east grid. So there's an independence to the decisions that you're making. You can make decisions over here, and you don't have to worry about them affecting one another.
But you're
But
saying you can do that with quantum or with the classical computing or both?
those two features, continuous variation and independence, make it easy for classical. But the direction that decentralized energy grids are going is that we have power plants throughout the network. People have solar panels on their houses, and they have cars with huge battery banks in their garages, which means that sometimes we're going to be pushing power into those areas of the network, and sometimes we're going to be pulling power. And then you do have a sort of flow in, flow out kind of decision to make. And every decision you make like that on the network affects all the decisions you make in the rest of the network.
Sure.
That's the kind of high dimensional optimization problem that quantum computers are really good at and classical computers struggle with. So that's the direction that we're going. In fact, if we want to, maximize our benefit of decentralized energy grids, we really need to look at these optimization techniques to make sure that process happens as quickly as possible. And that's an example, just to kind of help you understand. It's that binary decision making, where the decisions become related to one another. Those are exactly the kind of circumstances businesses run themselves into. In the case of Ford Otosan in Turkey, they were looking at their manufacturing processes for Ford Transit Line vehicles. And by using our systems, they were able to schedule 1,000 vehicles in 5 minutes instead of 30. And the
Aha.
reason why that, much faster time is important to them is because, they're trying to maintain their productivity and efficiency, but they're constantly getting changing circumstances. So they want to get that kind of agility incorporated into their business.
Interesting. Okay, so the changing circumstances really is the highlight of quantum. All right, say I'm a hypothetical CIO or CTO. How do I know
Yeah.
when it makes sense to invest in quantum exploration or pilots? Part of it is that I think there's still, correct me if I'm wrong on this, it's still a pretty small sliver really of enterprise that is using quantum. Maybe it's 1 to 3%, and I'd love to get your guess on that if you have a guess on that. But if not, I mean, how do I know if I'm an executive, is now the time to invest or explore a quantum?
Well, and a recent Wakefield survey we did actually with CIOs, you might be surprised to hear that like 80% of CIOs are looking or planning for incorporating quantum computing into their use cases. And that's because they're running into these circumstances of like operational optimization challenges where they feel that they've reached the limits of classical computing.
But that's
So
looking or planning, but you have a sense of actual application use out there?
well, yeah, for sure. It's
Okay, okay,
it's in the early stages. Yeah, I wouldn't say that it's like we haven't taken over an entire market segment or anything like that, but it's what's happening is that it's progressing extraordinarily quickly. As we're talking with folks, they're realizing that the technology, well, actually, this is actually a really key point. How do you make sense of the quantum computing industry, right? And when someone is
Right.
talking about a quantum computing product, right? Well, the first thing that you're looking for is, can you demonstrate that you can outperform a classical computer?
Sure.
So,
Right.
in D-Wave's case, we've performed some calculations in direct head-to-head comparisons with like classical supercomputers in the case of like magnetic material simulation, where those calculations would have taken the supercomputer as much electricity as the world uses every year, and we were able to do it on our quantum computers for less than $1 worth of electricity. So
Okay, so it's exponentially faster and better.
huge differences that are possible there. The
Yeah.
second thing is, okay, well, is the technology reliable enough that my enterprise applications can run on it? And we have a cloud service where our quantum computers have 99.9% availability and uptime,
Hmm.
so that it meets their requirements. Our quantum computers themselves have sub-second response times, and we have SOC 2 compliance. So that our customers can rely on us for those services. And then a third category that the businesses often look for is, well, who else is using this? And we actually have commercial customers using our quantum computers in their application workflows. And the two examples I talked about earlier, workforce scheduling and automotive scheduling, but also NTT Docomo in Japan is using us as they're optimizing the paging signals that pass between cell phone towers to cell phone users so they can, make sure that the signals are uninterrupted. Well, they've managed to reduce the number of signals they need to send by 15% during peak loads, which effectively increases the capacity of that network by 15%. And they're deploying that application across 250,000 base stations in Japan. So, that combination, we've called the quantum realized framework, which is, superior performance, high reliability, and exampled use cases. And we're working with a variety of companies and more every day to help them on that journey from identifying those applications, getting the business data that shows the advantages they can see, and then moving through their production release process.
All right. Well, how do you see the idea of hybrid approaches? So combining quantum and classical algorithms. Yeah, how does that shaping adoption? It's sort of like the hybrid car model. So like electric and gas hybrids came on the road really before all electric. Is that going to be the way quantum evolves, or not necessarily?
You're 100% right. In fact, it's going to be the only way that quantum computers are going to be used because
Oh,
we're bringing on a new computational resource in the presence of an existing one, right? And an established, mature computing technology. We
right.
don't want to reinvent the wheel. We're not trying to do the same calculations that they can do. So, most applications involve workloads for both of the technologies. And so we've actually built a platform which allows our users to send us problems where they can quickly and easily express them. And then we'll deploy both the classical and the quantum computers, accepting large portions of the problems, getting classical algorithms working across them, doing the quick searches that they do best.
Hmm.
And then they will actually make calls to the quantum computer on the customer's behalf, asking it instead of saying, well, here's the area I'm in. Can you make larger changes here that will help me move through the solution space more effectively? And then incorporating those answers for our users' behalf. And we're constantly working on improving that platform. So it's sort of like quantum computing as a service, quantum optimization, and business solutions as a service. And it means that, it provides a very reliable platform for them, and we're constantly working on improving it. So our incentives are really well aligned there. I think it's the right business model.
Well, I think I heard something and maybe make sure I understand it. Quantum computing as a service. I guess that's CQAAS. Do you mean literally logging on and accessing quantum computing? Or I would totally misunderstand that aspect of it.
Well, many of our users, I mean, that's a very good way of thinking about the application workflow. So there's going to be an IT team for whom they're just going to find this fits seamlessly into their information technology infrastructure, and they're going to be managing applications that are making calls to an API, and that hybrid service is just passing back high quality solutions.
Right.
That's where many of the businesses are interacting with our systems. But often, once we get to see how quantum computing technology is able to do useful work for us, then we're actually kind of a little bit more interested to learn more about it. And we've got an open source software development stack that then allows developers to dive as deeply as they'd like to go. And we also have direct QPU programming as one of the features in our cloud service. So, that it allows us to engage, I would say, like a broader swath of users. Often developers are working at the application layer, but
Mhm.
mathematicians might be working in the middle layer, and then physicists might be working at the lower layer.
Yep.
But there's an opportunity for everyone to kind of explore that whole ecosystem as much as they like.
Interesting. All right. So I think looking at the future is really interesting when it comes to quantum. I mean, how do you see it becoming really adopted? And we've talked about this, but will it be more of a niche specialty? Will it be completely mainstream? And I guess what I really want to know is when am I going to have quantum on my iPhone or just be able to access it on my iPhone? Like quantum computing on our iPhones in the year 2033, when is that going to happen? Or any other version of the future that you see?
Well, I mean, I can program quantum computers from my iPhone, and so in essence, people around the world can do that as well. And the other thing to keep in mind is that folks who are, in my area, when I order a 5 pound bag of M&Ms, quantum computing is involved in bringing that to my door. So
Now,
it's
now
it
how is that involved in the M&Ms?
well, so in that scenario, the schedules for the grocery delivery drivers that are determining, which days that they're going to be working and which deliveries they're going to be making, those are being quantum optimized by our technology.
Aha.
So as part of that flow of the coordination of the fleet of those grocery delivery drivers, that's happening with quantum computing technology, and then they run the routes, and it's the employees picking up the groceries and then them getting dropped off at my house. So that that scenario, I think, is very real, where we're continuing to interact with systems that businesses are driving to greater efficiency and productivity using quantum computing technology, and it just becomes a fabric of the IT infrastructure that exists in our lives. Um,
Hmm.
but there are organizations who are really trying to build national quantum capacity building, and, for instance, like the Jülich Supercomputing Center, which just launched the fourth largest supercomputer in the world and Europe's first exascale supercomputer. They have one of our quantum computers there, and they're in the process of developing all sorts of fantastic scientific research and also hybrid optimization algorithm development.
Hmm.
So there's really it's really affecting and kind of involved in our economy at a variety of scales for a variety of folks.
Mhm. Yeah, the really fascinating idea, I think, is quantum computing and artificial intelligence. Obviously, AI is already doing some really amazing things run by classical computing. When it is powered by quantum, it's like, well, quantum plus AI. Talk to me about that world a little bit.
Sure. Well, okay, so quantum computing and artificial intelligence are actually two very complementary technologies, and they share a lot of technical roots. There's probably maybe two categories that I'll introduce here for ways of thinking about it. One is that, AI on its own and Gen AI are transforming the way that businesses, generate insights and optimize tasks. But when it comes to making complex decisions in dynamic environments, they really run into their limits. So a lot of our customers are actually using quantum to optimize what AI recommends. So for example, if an AI system recommends promotional pricing because of a set of historical trends, it's actually a very difficult task to figure out the right combination of decisions across markets, products, and business constraints. But that kind of high dimensional optimization problem is exactly what quantum computing excels at. So they're very complementary in that workflow where they're each kind of doing different tasks. But we also have organizations who are looking at studying research papers which suggest that quantum computers can actually help make training more efficient for machine learning models. And Japan Tobacco's pharmaceutical division has actually implemented a quantum hybridized machine learning framework for discovering new drugs that's actually suggesting a larger proportion of valid drug candidates in their research. And the Triumph cyclotron is looking at how large particle accelerators like the LHC, how they can use our quantum computers to help them learn and synthesize and train models for detecting particles there, but in a more energy efficient way. So I think we're right on the cusp of a lot of really dramatic improvements there. That's an area we're exploring and working really hard. But certainly in the context where you know a business is forecasting the demand they're going to see and then using our systems to optimize their schedules to meet that forecast, they're already working in a complementary way today.
Mhm. Murray, I think you said it. It's fascinating. It's going to be a very, very interesting sector to watch. Thank you for shared expertise, and please come back and talk with us again sometime.
I'd love to. James, thanks for having me.